Hi, I'm Ian from Lynx Software Technologies. Welcome to another episode of Lynx in Action. With me, Dave Beal, Director of Product Management. Welcome.
Hi Ian, thank you.
Talk through what we can see here.
Sure. We have an autonomous driving car demo.
Okay.
There are two pieces to this demo. There's the simulated world environment. It's drawing the nice graphics on the screen to show the trees, the roads. It's also acting as the AI-based driving system.
Okay.
So this is determining how to steer the car in response to pedestrians or other cars or traffic or lane holding. Now, as we move to the right, this computer represents the computer that's actually resides inside of the car.
Okay.
This is doing two things in this case. It's running a Linux-based infotainment system.
Okay.
And it's also taking the inputs, the steering inputs, the accelerator inputs that are provided from the AI system and forwarding those inputs to the real-time operating system, which is actually in charge of the car's physical hardware.
Okay.
So here we have Linux running an infotainment system, real-time OS that's ultimately controlling the accelerator and the steering on the model car in response to that environment.
Okay. Maybe go into a little bit more detail on what platform architecture do we have there in the little yellow chassis, and you talked about Linux and RTOS. How's that partition on? Talk about the hardware side, number of cores, and how that all sets up.
Right. We have a 4-core Intel platform here.
Okay.
And it is running 2 Linux instances. The standard Linux, which is running the infotainment system. It also has a dedicated Linux designed to communicate with RTI DDS to the simulation system.
One of our partners.
One of our partners.
Yeah.
And then in addition, it has 1 core dedicated to running the ETAS RTA OS, which is providing the inputs to the car.
Gotcha. And okay, so it's all nice and behaving at the moment. You've got Linux running and you've got the real time. Anything else happen with this demo?
Yeah, it's we're running a single processor,
right,
with a non-critical infotainment system,
right,
as well as the critical system that's steering the car and braking the car.
Okay.
Now, what happens when little Johnny loads up a new game and it causes your system to crash?
I have children like that, yes.
Your computer might crash, but you don't want your car to crash. So the big red button here causes a fault within the Linux, causing Linux to crash. Right. And what we're showing is that the separation kernel hypervisor isolates the resources. Those resources used by the real-time OS continue to be dedicated and continue to run that software of the real-time OS. And that happens even while Linux reboots, after Linux crashes, or anything else.
Right, right.
Another feature that we have here is that Lynx separation kernel hypervisor allows very specific partitioning. For example, the infotainment system needs access to the GPU and the display unit. So we assign the GPU and the display to this operating system, and we assign only those peripherals and only that memory that's required by the real-time OS to support its function.
Got it, got it. And how does that functionality work in a real system? Is that sort of configurable on the fly once deployed, or is it more of a fixed constrained resources and that is what you get when you get it out of the box?
Yeah, we are focused on safety and security. Now, a system that has dynamic behavior, a system that can change its assignment or change its configuration during runtime, brings with it some pretty severe safety and security penalties. So Lynx Secure Separation Hypervisor configures the system resources at boot and then locks that configuration down.
Okay. So
So the resources that are dedicated to the real-time OS to drive the car remain with that real-time OS, and they can't be taken off or reassigned.
talk a little bit about how the Linux communicates back and forth with the rest of the system.
Yeah, sure. One of the really unique elements of our architecture is that we allow zero-copy communications between guests. The data doesn't go from one guest down to a microkernel, change context switch, cross the microkernel, up again, change the context switch yet again to get to between OSs. We go direct from OS to OS. It's a block of literally shared memory, almost like dual port RAM in the way we deal with that.
Okay.
And the ability to have zero copy between guests gives us very high performance and low latency. And by that I mean at the limit of the hardware itself. We actually support 3 primary families with our products. One is Intel, as we're demonstrating here. We also have ARM, ARM v8A, and that is instantiated in NXP, Lynx parts today across A53 and A72 architectures.
Okay.
We also have PowerPC support with the T2080. So our customers have a really broad choice of hardware architectures with which they can set up redundant systems or deploy previous legacy software into newer based systems.
Great. Dave, thanks very much.
Thank you.